Welcome to High School Geometry with Netz and Weichel. This is Mrs. Netz.
This is Mrs. Weichel.
And today we are covering 3.2, What Makes a Triangle? Our learning target for today. What we are learning is by the end of the lesson, I will be able to show if it's possible to create a triangle from any three line segments. Why we need to learn this? Understanding the inequalities and the relationships within a triangle that reveal the information about triangle sides and angles is very important. You can't just take any three segments and make a triangle out of it. How you will know you know it? Well, you'll know you've mastered it when you can determine, when given three segments, if they indeed will make a triangle.
Very cool. All right, let's go ahead and get started. So first, what is a triangle? If you remember from chapter 1, a triangle is a polygon with 3 vertices and 3 sides. So I have given you a blank triangle on your notes. Go ahead and label it TRI. And TRI are your 3 vertices. So you have point T, point R, and point I. So go ahead and list your vertices as T, R, I for triangle. Your sides, if you remember, sides are going to be segments. So segments, you have connecting points T and R. So TR is one side of your triangle. We have side RI, and we have side TI. Remember, when naming a segment, you need to use 2 capital letters, which are your end points, and you need to put the little dash over the top. It is not incorrect to name side TR, side RT. It is not incorrect to do IR or IT. That is completely 100% up to you.
Now, Mrs. Weichel, if I had named the vertices angle T, angle R, and angle I, would that have been okay as well?
Remember, the vertex is the vertex of the angle. So if you were naming the angle, angle T, angle R, angle I, that would not be wrong. The vertex is just a single point, so it is not incorrect necessarily to have that there, but a vertex is just a point in the angle. So by having us name the vertex, I'm looking for just that single point.
Awesome.
Okay. Now we're going to do a lovely proof. We're going to explain something we all know coming into this class. We all know that angles in a triangle have a sum of 180 degrees, but let's explore why that is. So the first thing we know, or the first thing we're going to do, is we're going to, with your straight edge, we're going to draw a line. And I want that line to go through point J. And because we need 2 points, I'm going to go ahead and just name the second point K. Just kidding. No, I really want you to do it. Go ahead and do it. So we have point JK, or line JK. And we're going to go ahead and draw it so that it is parallel to RW. So draw it in a way that we are able to say that they are parallel to each other. So I'm going to go ahead and put my arrows on here. So here's 1 arrow and 2 arrows. So I'm showing in the diagram that line JK and RW are parallel. The reason we're able to do that, basically it's just a description. You can read what I have here. It's through any point not on a line. There is 1 line parallel. So point J is not on line RW, so I can draw 1 line through J that is parallel to RW. That's what that means. And what that does is it makes some more angles. So we have angles 1, 2, and 3 already given to us, so I'm going to go ahead and have you guys all right now make this angle right here, this obtuse angle. I'm going to go ahead and say that it is angle 4. And then I'm going to go ahead and have you draw that this acute angle right here that we just created by drawing this line, we're going to go ahead and say that that is angle 5. So now our next step, if I know that these lines are parallel to each other, there are 2 conclusions that we can now make using something that we learned in lesson 3.1. When you have parallel lines cut by a transversal, there are some angles that we know are congruent. We have JR as a transversal with my 2 parallel lines, so we would know that angle 2 is congruent to angle 4 because they are alternate interior angles. We would know the same for angles 3 and 5. Angle 3 would be congruent to angle 5, and angle 4 would be congruent to angle 2, The reason parallel lines make congruent alternate interior angles. So now we're trying to prove that these angles add up to 180 degrees. So we need to look at our picture to see if we can come up with a reason why we can say that. Well, if you look, the reason I had you draw this line, look at what we have right here. Oops. Look at what we have right here. You've created three angles that are all meeting up at point J and spreading out to make straight angle J. What do we know straight angles add up to equal? Or straight angles equal?
180 degrees.
So would it be safe to say that angle 4, 1, and 5 would add together to make 180 degrees?
Well, yes, because all three of them are on the same line, sharing the same vertex.
So I went ahead and wrote an equation. I know that angle 1 plus angle 4 plus angle 5 is equal to 180. Now, again, remember our goal. Our end game is to get the angle 1, 2, and 3 add up to 180. So if you look at our two lines, line 2 and line 3, we have some important information happening here. We know that angle 4 and 2 are the same. Well, I have angle 4 in my equation, but I want angle 2 in my equation. I also know that angle 5 is congruent to angle 3. I have angle 5 in my equation, but I want angle 3 in my equation. So I'm going to go ahead. The reason some of you may see the end already, we do need to go ahead, since we're writing equations, we're going to go ahead and say that because I know the angles are congruent, I know they're equal in measure because that is what congruent means. So now you can use a property that we learned back in Unit 1. If I want 2 in here, what could I do? If I want 3 here, what could I do? What could I use?
I would then say use substitution. Just
And
substitute one in for the other.
By substituting in one for the other, you end up getting your equation that we were looking for, which is not what I have typed here. I think I was tired when I was typing this. So, well, I'm actually going to do the substitution. What do I know angle 4 is the same as?
You know, angle 4 is the same as angle 2.
So we're going to go ahead and say that that is 2. What do we know angle 5 is the same as?
Angle 3.
Which actually creates angles 1, 2, and 3 having a sum of 180 degrees, which is the triangle sum theorem. So
Awesome.
there you go. All right, moving on, go ahead and turn your page over. Exterior angles, this is just a review from Unit 1. Exterior angles are angles formed by a side of a polygon and an extension of an adjacent side. So if you look here, we have this side of our triangle, and then we have the bottom, which we have extended out past the vertex, and what that does is it creates angle 4. So we can say that angle 4 is an exterior angle to this triangle. Now a new vocabulary word, remote interior angles. Remote interior angles are angles not forming a linear pair with the exterior angle. So again, looking back here, we know that angle 4 is our exterior angle. We know that angle 2 is forming a linear pair with angle 4. So what are the other two angles?
1 and 3.
So we can say that angle 1 and 3 are remote interior to angle 4.
I kind of like to think of it as angle 4 is my remote control, and it's aiming at my remote interior angles, which is
good.
1 and 3.
There you go, because if it was 2, you could just touch it. You wouldn't need a remote control.
Well, that, and I already have a vocabulary word for 4 and 2. They're a linear pair.
Oh, that's true, too. All right. So now you have a theorem, exterior angle theorem. So let's go ahead and talk about two things we know. What do we know about angle 2 and 4?
Well, they're a linear pair. So therefore, when we add them together, they must equal 180 degrees.
So we know angle 4 plus angle 2 equals 180. Now, today, we've talked about the triangle angle sum theorem. What do we know about the angles inside of a triangle?
Well, we know this from looking at proving, which one was it, Mrs. Weichel, that we learned that using triangles inside other shapes, we could figure out the sum of the angles.
This is when we did the sum of the interior angles.
Yes.
The n minus 2 times 180. And we also just did it here, where we proved that angles in a triangle have a sum of 180. So we've actually spent a few days in this course going over the fact that the interior angles of a triangle add up to equal 180.
And
Pretty important.
Hopefully our students are realizing we keep talking about triangles a
Triangles
lot.
are super important. So these two equations for the same picture are true. So if both the left sides are equal to 180, what would we know about the two left sides? If they both equal the same thing.
That we can
That they must
equal each other, so that
There
means
you
we
go.
could, well, I was going to say we could substitute, right?
So we could substitute in the left side up into 180. So then we would have angle 4 plus angle 2 is equal to angle 1 plus angle 2 plus angle 3. Well, if angle 2 is on both sides, what would happen to angle 2?
Well, it would cancel out, wouldn't it?
Exactly. So what you're left with is that the exterior angle, which is angle 4, is going to equal the sum of the remote interior angles, which is angle 1 and angle 3. And again, the evidence to this theorem is right here in these two equations. Both angles 1, 2, and 3 add to equal 180, and angle 4 and angle 2 equal 180. So therefore, these two equal each other. Canceling out 2's, you're left with angle 4 and angle 1 and angle 2. I'm sorry, angle 3.
Perfect.
So there you go. And then you're going to be able to use that now to find missing angle measurements. If you're given 2 of them, you should now be able to find the third. The last thing we're going to talk about today is the triangle inequality theorem, which goes back to our learning target today. The sum of two sides of a triangle must be greater than a third side. So in order to create a triangle, if you were to measure with a ruler all three segments, the two shorter sides have to have a sum greater than the third. So you can see here I have 3 different color segments. I'm going to show you an example of why it would not work. This green one on the bottom is going to be one side of my triangle, and then I'm going to try and make a triangle with the pink and the blue sides. So I have to put this at the ends because triangles meet at the ends. So if I go here, and then if I come over here, whether if I put it here or here,
there's no way
they're ever going to meet up. That is what this theorem is explaining.
I would also like to encourage anyone who is watching the video and not participating in class for this lesson to go and find something that you have that you can use to kind of play with this. I would say either like straws or toothpicks. So for example, if you all you need is 2 toothpicks, so hopefully they're both the same length, I would just take one of them and cut it in half. And you'll notice if you cut one of them in half, and it doesn't even have to be exact, when you go to try to make a triangle out of the 3 pieces, you'll find it's impossible.
It is impossible. And then if you want to experiment with something longer like a straw, you could actually make one that works, and you can see all the different types of triangles you can make given 2 shorter sides adding together being bigger than the third one.
So a little bit of a reason as to why cutting the toothpicks in half and then trying to make a triangle with the third piece being whole, why it doesn't work. If you think about it, if you have to make all of them meet end to end, so you have your whole toothpick that you didn't cut, and then your other 2, if you make those other 2 meet back at where you cut them apart, and then you try to get their ends to meet with the other ends of the toothpick that you didn't cut, you'll find it ends up just making 2 straight lines.
Yeah, and you can kind of see that here with this triangle. Right now, this side and this side, if I were to flatten it out, it would be longer than that third side. And as I stretch it out, you can see it ends up making a single line, which is what Ms. Netz was just talking about.
With the toothpicks.
All right, so I was just going to give you an example, excuse me, of 2 possible types of problems you could see with this. One is if I give you 3 side lengths, could they make a triangle? So a possible problem could be something like this. You could have 2, 4, and 5. So does 2 plus 4 equal something greater than 5?
So 2 plus 4 is 6. 6 is definitely greater than 5. So because 6 is greater than 5, This would definitely work.
That would work. An example that would not work, go ahead and make this a little smaller, would be if I went 1, 2, 3. 1 plus 2
Is 3.
is not greater than 3. So no.
So remember, equal won't work. It has to be greater.
The other type of problem that you can see with a problem with one of these is you'll get 2 side lengths and you'll be asked to find a possible third. So if you're given a length of 5 and a length of 8, there is a range of possibilities for what that third one could be. So what I always suggest is make the third one x. And you're going to basically make 2 inequalities that you're going to be solving. So if x is the smallest side, what would I add it to? Remember, you're always adding the 2 smaller ones together. So definitely 5, because 5 is smaller than 8. So if x is the smallest, 5 is the next smallest, it needs to be greater than 8. Think back to when you first learned inequalities, first learned basically one-step equations. You would simply subtract 5 from both sides, giving you x must be greater than 3. Now let's say that x is the biggest side. If x is the biggest, then 5 and 8 must be the 2 smaller sides. So in a separate problem, you would then do 5 plus 8 must be greater than x. 5 plus 8 is going to be 13. That must be greater than x. So there's our range. The way you're going to see it written is as a compound inequality.
So basically, x has to be somewhere in the middle of these 2 numbers. So what you're going to do is you're going to go ahead and put x in the middle, and then always put your smaller number on the left and your larger number on the right. Then you're going to write 2 inequalities, and go ahead and write them separately, but always read from the x value. So for example, if we look at x, we know x has got to be bigger than 3.
Now use the symmetric property, go the other way. If x is bigger than 3, then 3
has to be smaller than x. So we're going to use a less than symbol. So then on the other side, we know that x has got to be smaller than 13. So that one's a little bit easier to write because we know to write that we just say x is less than 13.
So there you go. That's how you would write your answer for a range of possible sides. Hopefully you feel confident in everything we went over today. Your triangle inequality theorem is what we just went over, with the 2 smaller sides needing to be greater than the third. Your triangle exterior angle theorem, that's going to be when your remote interior angles add up to 180. Hopefully you feel confident in using that. These keep coming apart. Very sorry about that. And then lastly, hopefully you feel good about the triangle angle sum theorem, which is just that 3 angles in a triangle have a sum of 180 degrees. If you have any questions, as always, please make sure you reach out to myself or Mrs. Netz through Remind or email.
Hey, Mrs. Weichel.
Hey, what, Miss Netz?
Why did the right triangle go to the beach?
Why?
Because it was 90 degrees.
Ah! Thanks for joining us. We will talk to you again in lesson 3.3.